define a number of dimensions by which creative systems can be characterized. It's not easy because there are an astonishing variety of generative systems. Here, we restrict ourselves to computational and digital systems. The first dimension we can look at is the domain in which the system operates and the creative task it partially or completely addresses. Examples of domains include poetry, music, visual art, cinema, dance, video games, animation, humor, gastronomy, design, architecture, etc. Creative tasks are also very varied. Examples of creative tasks include portrait drawing, joke making, etc. In music alone, we counted over 20 different tasks for which we know generative systems. For example, the composition tasks, the interpretation task, and the improvisation task. Sometimes new tasks are put forward that did not really exist before. For example, the continuator, with its particular interaction protocol, is doing something that musicians typically don't do. Musical continuation might be a new creative task. Some systems include multiple tasks, achieving several creative tasks in sequence or in parallel. To apply these concepts to the examples we've already seen, Aaron's domain is visual art and the continuator's domain is music. Aaron's creative task is painting and the continuator is to improvise, by making continuations in the style of what was played to it before. Another dimension of generative systems is the genericity or generality of the system. Some systems are very specific to a particular domain and task and might have an identifiable aesthetic. For example, Aaron is very specific. Even though it can generate an almost infinite number of paintings, after having seen enough of its productions, you can distinguish Aaron's styles pretty precisely. Some other systems are more generic. For example, the continuator works independently of the style of the music or the musician that is playing, whether it's classical music, jazz, or pop music. The continuator does a task called style imitation. Style imitation can be defined scientifically as the idea that given a corpus of artifacts C, with various examples of artifacts representative of a style S, the task is to generate new instances that would be classified by an unbiased observer, that is you or me, as belonging to that particular style. So we have systems varying from very specific to very generic, and that has implications for the computational creativity community because it means that work and research within the community can range from purely artistic work to purely scientific work. Often, artistic systems are more specific. They have strong aesthetic anchored by the artist. Research in computational creativity tends to aim at systems that are more generic. Because computational creativity systems are very interdisciplinary, all combinations in between those two extremes are possible and can be found. Another dimension of generative systems is the level of autonomy of the system. On one end of the continuum, we have systems with no autonomy whatsoever. They are not generative. For example, when you open a word processor software, nothing will happen if you don't click on a button. That's usually the case for most creative software. On the other end of the continuum, we have systems that are completely autonomous. Aaron, for example, paints new paintings on demand without any further input beyond all the work that his creators put into it. In between these two extremes, you have a variety of systems that automate only part of the creative task. Systems for computer-assisted creativity or creativity support tools often fall into this category. They exist in various domains like computer-assisted composition, computer-assisted animation, and computer-assisted design, to name just a few. Levels of autonomy are very important to consider. The idea of giving the machine some autonomy is one of the strong links between generative art and research in artificial intelligence, machine learning, artificial life, and computational creativity. It is the transfer of autonomy to the machine. Some systems have autonomy, but also interact with humans. The interaction can be in the context of a particular creative task, like with the continuator that establishes a sort of dialogue with its user musician. Another case of interactive systems are systems for computer-assisted creativity or creativity support tools. Interactivity and human-computer interaction in general is a complex topic that is well beyond the content of this class. But let's say a few more words about it before we move on. Whether they are purely generative or not, generative systems can be interactive or not. For example, Aaron is not interactive, while the continuator is. In art, we say that an artwork is interactive if the audience influences the unfolding of the artwork in any way. There is at least two types of interactivity. There is low-level interactivity, which is the usual meaning of the term. A system is interactive if it takes input in real time. Computers and most software are interactive systems in that sense. In human-computer interaction, the system takes input and these inputs are mapped to some effects or system's action. For example, we can interact with a text editor to write a poem, or we can interact with a video editing software to make a montage. In this case, we are just using the interface to tell the system what we want. The input is directly mapped to a set of actions, reactions of the system. The mapping can be more or less complicated, and many artists have been developing interactive pieces using this mode. Net art offers a wide range of approaches using this type of interaction. Sometimes, low-level interactivity is called reactivity because the system acts in response to something you did. But there is also high-level interactivity, sometimes called agent interaction or conversational interactivity. Agent interaction is where the actions of one agent influence the actions of another agent and vice versa. Interacting is not something that an agent can do alone. It takes at least two agents for them to interact. This is the case when two people are dancing tango together, or when two people are having a conversation, or even when the jazz player plays with the continuator. There is an interaction because the actions of each of the agents influence the actions of the other agents. We can't really predict the actions of each agent with any degree of precision, but we just observe their interaction and describe its emerging form. There can be interactions between natural agents or between natural and artificial agents. We'll come back to the notion of artificial agents in a few sessions. The fact that there is a reciprocal action or influence of each agent on the other is what differentiates high-level interaction from the more deterministic manipulations of so-called interactive interfaces. In generative art and computational creativity, we will encounter systems that cover the wide range of levels of interactivity. Another dimension of generative systems is the relationship to time. Some systems are online, and there are various levels of real time. For example, the continuator is an online system that plays in real time with the musician, even though the interaction protocol that the system is using was generated ahead of time. Other systems are offline, they can be generated ahead of time, and the generation itself can occur slower or faster than real time. For example, Aaron is an offline system because the painting is made ahead of time. Although this is open to discussion since it paints in what appears to be similar to human painting time and can be considered to work at the pace of an artist. However, it can also paint much faster than a human if it's told to do so. In general, it can be considered an offline system. Then, the origin of the system's knowledge is to be considered. The knowledge can be encoded in the system by its author, in which case the system may generate from scratch using only knowledge encoded through rules. Aaron is such a system. Or the system can take input. This may be a set of parameters and settings in a parametric system, or there may be a full data set that is provided. For example, in data art or visual arts, some systems are generative but take a dataset as input. Finally, the system's knowledge may be learned, that is, extracted from the input. A very well-known type of system in that category is a corpus-based system, where the system has been exposed to existing material. For example, in style imitation, the samples from the target style are what the system extracts the knowledge from, as when the continuator learns from what the jazz pianist is playing. The knowledge of the system can be static or dynamic, and the system's knowledge can change over time or not. The output of the system is another way to characterize a system. The output can be unique, but most often it is not. The diversity of the output has to do with the level of generality and scope or specificity of the system. Aaron has a well-defined style, while the continuator is not bounded to a particular musical style and works fine with musicians playing in radically different styles. So they have different diversity of output, even though they can generate almost ad infinitum. Generative systems can generate all sorts of output with more or less diversity, and that's the case with both Aaron and the continuator. Finally, there is system pattern of behavior, and that is of central importance. The sheer diversity of systems' behavior makes it hard to characterize, especially without a complete knowledge of the algorithm and parameters that are used. One can, however, observe pattern of behavior. One famous classification is the one proposed by American computer scientist Christopher Langton, who is one of the founders of the field of artificial life. Langton distinguishes 4 classes of behavior that systems can exhibit: fixed, periodic, complex, and chaotic. Fixed behavior is where the system converges to a static output. Periodic behavior is where the system enters into longer or shorter patterns of recurrent behaviors. Then you get systems that exhibit chaotic output, where the behavior of the system appears to be random and there's no discernible pattern. At the frontier between periodic and chaotic systems are complex systems. This is the sweet spot in which we find the most refined structures, such as the structures emerging from intelligent and creative behavior. It is good to note that a given system can exhibit all of these behaviors depending on the circumstances. We will see examples in the next session. Furthermore, some systems are adaptive as well, which means that they change their behavior or type of behavior depending on their context and previous experience. By complex systems, we are talking about the complexity of the product of the system, its output. We do not mean the algorithmic complexity of the system, which is the time complexity of the algorithm in terms of numbers of operations it has to execute to perform its task, nor space complexity, which is the amount of memory needed for the algorithm to complete the task. The system complexity does not refer either to information theoretic complexity, which has to do with how compressible a particular set of information is, nor with Kolmogorov complexity, which is the length of the shortest computer program in a predetermined language that produces the output or behavior. What we are talking about is effective complexity, a term that refers to the internal work of the system as well as its external behavior. In fact, effective complexity of the output can be plotted as in this figure adapted from Philip Galanter, who himself adapted it from Gary William Flake. The effective complexity peaks when the output is complex, but falls near to zero when the system's behavior is either constant or completely random or chaotic. The effective complexity of the system is not to be confused with the complexity or sophistication of the system itself either. We will see many examples of simple systems with very high effective complexity. The various types of behavior and levels of autonomy of the system are commanded by the system's architecture. While it is difficult to generalize, we can isolate the following archetypal approaches of architecture: generative and evaluate, generative with reflexive feedback, and interactive and adaptive system. First, we have a simple generative system. It optionally takes some input parameters, but then is a self-enclosed system that just generates new artifacts, actions, or behaviors for the user or the audience to enjoy. The second type of architectures involves architectures with a reflexive loop, when there's a loop between the system and itself. A system can be divided with one part that generates artifacts and another that evaluates them, selecting some as being creative enough, that is novel and valuable enough, to be presented to the audience. This is reminiscent of the notion of brainstorming. Brainstorming was an idea introduced by the American advertising executive Alex Fechner Osborne in his book Applied Imagination in 1957. One of the chapters described brainstorming, which is the idea of dissociating the production or imagination of novel solutions and artifacts from the evaluation, selection, or decision about the value of the artifact when searching for solutions to a given problem. Osborne's technique is very precise, but it rests on 4 rules. Number 1, go for quantity. This rule means you should enhance divergent production, aiming to facilitate problem solving through the maxim, quantity breeds quality. The assumption is that the greater the number of ideas generated, the bigger the chance of producing a radical and effective solution. The second rule is without criticism. In brainstorming, criticism of ideas generated should be put on hold. Instead, participants should focus on extending or adding to the ideas, reserving criticism for a later stage of the process called the critical stage. By suspending judgment, participants will feel free to generate unusual ideas. The third rule is to welcome wild ideas. To get a good and long list of ideas, wild ideas are encouraged. They can be generated by looking from new perspectives and suspending assumptions. These new ways of thinking might give you a better solution. The idea is to encourage ideas without thinking about their feasibility. The fourth rule is to combine and improve ideas, as suggested by the slogan 1 + 1 = 3. It is believed to stimulate the building of ideas by a process of association. This last rule reminds us of the idea of combinatorial creativity we discussed earlier. It has been shown experimentally that this simple decoupling of the generation phase and the evaluation phase is actually productive. People working under the constraint of finding good ideas or solutions produce fewer interesting ideas than people using the brainstorming technique. This was shown by Parnes and Meadow in a 1963 study. However, in 1999, a review of brainstorming research counted over 90 studies looking at a variety of dimensions of brainstorming in a variety of contexts with mixed results. So that's the second type of architecture. The third type of architecture is interactive or adaptive systems, which are simply looped systems that have a feedback loop with their environment. Independently of their inner architecture, they don't only generate artifacts, actions, or behaviors that are delivered to the world, an audience, a user, or an environment, but they also can sense or perceive this world, audience, or environment, including their own production, and that can inform their later production. For example, the continuator falls into this category, while Aaron falls into the first category of simple generative systems, also sometimes called merely generative systems. There are plenty more architectures, and we will come back and deepen these topics several times in the rest of this class. In this class, we will describe the generative and creative processes that we will cover by describing the algorithm that make up the system modules. We will study many such architectures and algorithms in the rest of the course. More specifically, we will look at computational creativity in the context of creative tasks, artist practices, video games, digital performance, design, etc. We will not look specifically at computational creativity or generative systems in science or engineering, where they also exist. Some of the algorithms we'll see are used in generative systems in engineering and science. However, the tools for both art and science are the same, and the ideas and theoretical analyses are often similar. In other words, this course has a very large scope of application, and most of the algorithms we will study will eventually be relevant beyond artistic practice. To summarize this section on classifying creative systems, our typology distinguishes the following elements of a generative system in generative art or computational creativity: the domain in which the system works, the creative tasks that the system addresses, the genericity of the system, how specific or generic it is at achieving these tasks, the nature of the system, whether it is more artistic or scientific, the level of interactivity and the type of inputs that the system can use and where it derives its knowledge from, the level of autonomy, the system's relation to time, its behavioral complexity, and finally, the architecture of the system and the various algorithms it uses.